All right, let's make sure it's presenting. Okay, is it in the presentation view for you guys?
Oh yeah, this is great.
Okay, awesome. So I have some slides on polymers first, and then I'm going to talk about some polymer-derived ceramics kind of at the end. So just kind of an introduction first. So polymers are large substances which are composed of molecules, which are monomers, the smaller sections here, that are linked together through chemical reaction. And polymerization is the name of the chemical reaction, which is going to combine those monomers into polymer chains. So as you can see in figure 2 here, I'm kind of highlighting a monomer. This is a figure of DNA. So this monomer, once it goes through some polymerization, it's going to form this long polymer chain, as you can see here. And again, polymers can be found in nature, such as DNA, or they can be manufactured as well. And then figure 1 here shows some different structures of polymers, which I'm going to talk about on the next few slides. So linear polymers are simple polymers that are composed of repeating monomer units. So you can see up here, it's very simple, no branching or anything. And due to the linearity, their properties are that they have high density, high tensile strength, and a high melting point because they can arrange in a very organized fashion, so that can help contribute to these properties. And some common applications of linear polymers are high density polyethylene, which is what makes up milk bottles, and also polyvinyl chloride. And then in figure 3 here, you can see an image of some linear polymers. And if you look in B specifically here, you can see these individual kind of structures that don't have any branching. They're just kind of on their own here. So this is actually part of a DNA segment. And then branched polymers are linear polymers that one monomer unit is replaced by a polymer chain. So you can see up here, they look like linear polymers, and then they do have a little bit of branching. You can also see that in figure 4 over here. Again, they look pretty simple, but they do have some excess monomers on the side in their branches. And due to this branching, they cannot arrange in an organized fashion such as the linear polymers can. So that is going to contribute to them having lower density, tensile strength, and melting points as compared to the linear polymers. And then low density polyethylene is an application of these branched polymers. So that's kind of when you think of like a weaker plastic, or kind of when I think of a weaker plastic, because it's going to have that lower tensile strength and density. So plastic bags and bubble wraps are examples of branched polymers. Then you have cross-linked polymers. So these are going to be chains of polymers that are linked together through covalent bonding, which is going to form a more complex structure. So you can see up here, it kind of looks like some branched polymers that are starting to come together more. And you can see that here as well. This is like a branched polymer that's going to have a covalent bond with another branched polymer, and that's going to form those cross links. And lightly and moderately linked polymers are going to be fairly elastic just because they don't have too much holding them together. And some common applications are vulcanized rubber. So starting to get into like a harder plastic when you're kind of thinking of real life applications. So like tires and shoe soles, and also hockey pucks here are made from vulcanized rubber. So those are going to be cross-linked polymers as well. And then lastly, we have network polymers. So these are polymers that are much more elaborately cross-linked, and the cross-linking is going to inhibit the movement or the mobility, and it's also going to give strength. So again, these heavily linked polymers are going to be pretty rigid and have very, very high melting points. So some common applications are Bakelite. So I guess when I think of some harder plastics, that those are going to be composed of some network polymers. So you can see up here, they're cross-linked in all different directions, and that's again going to give that complex structure and that rigidity. And then the classification of polymers can kind of be thought of as thermoplastics, elastomers, and thermosets, and this is based on their structure and their mobility. So thermoplastics, I have in parentheses here because, again, I've talked to Dr. Singh about this. He says not to use the word plastic too much, but I guess thermoplastics are what I think of when I think of plastics. So again, these are going to be linear and branched polymers, so plastic bags, water bottles, that sort of thing. And they can be formed and reformed by melting. So upon heat treatment, they're going to turn back into liquid, and that makes them highly applicable for certain industries because they can form them and reform them. And they do have weak intermolecular forces, and they can be either crystalline or amorphous. So if you're going to heat up a thermoplastic and melt it down, sometimes upon cooling, it's going to become amorphous, which you can see here it has little to no organization in its structure. But sometimes when it cools down, they can form these semi-crystalline structures. So that is under thermoplastics. And then elastomers are going to be very lightly cross-linked polymers. And because of that, they're going to be ductile and undergo mostly elastic deformation. And then you get into thermosets, which are those highly cross-linked or networked polymers. And so they're going to change chemically during the setting process or the cooling process. And so they can't be reformed. You can't melt down a thermoset again after it's been kind of set. And then again, they're going to have rigid structures, which is going to inhibit their movement. And then now I'm going to talk a little bit about polymer-derived ceramics. So this slide is just kind of some history and recent development of PDCs. So PDCs have been studied for over 50 years now, and kind of the late 60s and 1970s was the first practical applications of PDCs. And I believe that was just with some polymer-derived ceramic fibers. And more recently, as you can see in figure 9 here, the interest and publications in PDCs has kind of skyrocketed in the last 10 or 20 years. So in 2009 to 2018, there have been about 1,600 publications about PDCs, which is more than all of the publications before. So you can see that that's really increasing. And then this inset graph here is publications of free carbon, which I'm going to be talking about next week, but this is just my same schematic that I used in that slideshow. And PDCs are garnering interest in many fields. And then some kind of recent developments, nanocomposites have begun to be produced via the PDC approach, and also some silicon-free PDCs have been developed as well, such as boron-based preceramic polymers and other ones as well. So organosilicon preceramic polymers are going to be materials that are polymeric during their first stages and their shaping, and then through heat treatment, they're going to turn into ceramic, which can give advanced ceramic products that have many uses and advantages. So again, they're going to start with that polymeric precursor, which you can see in figure 10 here. So if you start with that silicon and then you add nitrogen, you're going to have a polysilazane precursor, and etc. You can see all these kind of classes of preceramics here. And so the advantages of using the polymer-derived ceramic method as opposed to like a powder method for making ceramics is that they can be shaped using polymer forming methods, such as drawing. And that is going to allow your ceramic to have a much more detailed or complex structure. And that is a good thing, because if you use a different method of just like starting with a powder and turning it into ceramic, and then if you try to increase like the complexity or the detail with that using tools, you're going to have a lot of tool wear and fracture. So it's a lot more advantageous to start with polymer, form it in the polymer stage, and then heat treat it until it becomes a ceramic. And so they also have low synthesis temperatures when they're in the polymer stage, and then you can modify the molecular structure by chemical reaction. As you can see here, all of these different precursors do have different chemical makeups. And so with that molecular structure here, there are two aspects of a polymer structure which are going to change its class and its properties. So if you look at figure 12 here, if you're changing the X group, that's going to change the class of the polymer, or the precursor. So these 5 kind of arms here on figure 11 are kind of 5 main classes of preceramics. So you have polysilazanes, polycarbosilanes, polysilanes, etc. And as you can see, when you're changing the X group, that's going to change the class. So here the polysiloxane has just oxygen as its X group. But the polysilane has no X group. So that's kind of the difference between these classes. And then moving kind of forward from that, as you change the R groups on the sides here, that's going to further change the properties of the class of the pre-ceramic. So like within this class, as you're changing the R groups, you can change the electrical properties, the chemical properties, etc. All of those properties can be changed. And then as for the process of kind of turning a pre-ceramic into a ceramic, so first you're going to start with polymerization. So you're turning this monomers into kind of polymers, and then you're going to do the shaping at this stage, so while they're in the polymer stage, and then cross-linking will occur, and cross-linking can occur at very low temperatures, again, because of the polymeric nature of the precursor. So between like 100 and 400 degrees Celsius, the polymers that I'm working with right now have been cross-linking at around like 180 to 200 Celsius, so it's in that range. And then again, that shaping can be completed by plastic forming techniques when it's in the polymer stage. And then cross-linking is going to cause the formation of these 3D networks that you can see here, and it's going to turn the polymer precursors into thermosets. So then you have pyrolysis and annealing. So if you look in figure 14 here, we start with the polymerization, shaping, cross-linking, and then you move on to pyrolysis as the temperature goes up, and then annealing. So pyrolysis is going to turn those pre-ceramics into amorphous ceramics by like the reaction and the elimination of organic groups, and this can generally be complete below 1100 degrees Celsius. And then this is going to lead to some oxidation and some shrinkage. And then further heating through annealing is going to cause some crystallization of those ceramics. So that's going to reduce the stress generated by that shrinkage. And so that can kind of further change the molecular structure of your ceramic at that point. And then lastly, I'm going to talk about some applications. So fibers are one of the most successful commercial applications of PDCs because they're lightweight, they're durable, and they have they can withstand very high temperatures. So in figure 15 here, I have a picture of a jet engine, and some of these components can be reinforced by fibers or by ceramic matrices. So for example, the blades here of the jet are going to need to be able to withstand some pretty high temperatures because of the speed and the temperature that they're going to be working at. So a lot of times these can be reinforced by fibers or by other methods of PDCs. And then coatings are often used to provide protection for surfaces, which will allow them to withstand extreme conditions. So similarly to what we talked about here. And then lithium-ion batteries are something that I've kind of worked with in the lab, and I think it's interesting that the polymer-derived ceramics can be used for anode materials because of their chemical stability, and they also have some reactions with the lithiation and the delithiation of the cell. So yeah, that is what I have for today.
Okay, very good.
Thank you.
Thank you, Mabel. You see, looks like she's off to a good start. You know, it helps to start in spring. You know, not in summer. So you have 5-6 months of learning, and then you can understand these materials better.